Today, we're diving into the world of fluid and smoke simulation. It's pretty cool stuff.
Yeah, it really is. Our mission for this deep dive is to unpack exactly how these dynamic visual effects, how they're brought to life. We'll be focusing specifically on the individual shaders. These are the little programs doing the heavy lifting, the calculations that turn abstract data into, well, convincing movement on screen. You can think of it like understanding the gears and levers inside some complex, constantly moving machine.
Okay, that sounds technical, I admit. But we promise we'll make it crystal clear. We want to reveal the clever design behind these digital flows. By the end, you'll have a whole new appreciation, I think, for the artistry and the engineering that makes these simulations possible. So where do we start? Let's look at the very foundation, how these things actually work.
Right. So at the heart of a fluid simulation, you basically have two main data structures. They're often represented as textures, like images, but holding data. And they're constantly being updated. Our source material calls it a ping pong system, which is a good way to put it. You essentially have two versions of each main texture. This lets the system calculate the next state of the fluid on one texture while the current state is being displayed from the other. Then, boom, they swap.
They swap really fast, I guess.
Instantly, frame by frame. It's like having two identical canvases. While you're busy painting the next scene on one, the audience is looking at the completed one. Then you just switch them in a blink. Keeps everything smooth.
Okay, got it. So what kind of information are these textures, these digital canvases, actually holding? What's stored in there?
Good question. So one texture is mainly about the velocity of the fluid, basically where each little bit is moving and how fast. It also stores pressure information, which is really crucial. The other texture holds the color or tint. Sometimes it's just called dye. Think of the actual color of the smoke or the fluid.
I see. So it's like a canvas that doesn't just have paint, but also these invisible arrows showing flow direction and speed and maybe like pressure points.
Exactly, and pressure points, yeah.
And crucially, these aren't static images. They're changing constantly, every single frame, which gives us that feeling of smooth, continuous movement.
Precisely. Fluid simulation is inherently iterative. It's a cycle, a continuous loop of calculations. And these calculations are done by those specialized programs we mentioned, the shaders. There's a central update process that kind of orchestrates the whole thing, making sure each shader runs in the right order. Each shader has a very specific job. It takes the output from the previous step, does its calculation, and feeds its result into the next step. It really is like a carefully choreographed dance.
Okay, let's unpack this dance then. Shader by shader. Imagine starting a painting, right? You put down the first splashes of color, maybe hint at some initial motion. Is that kind of what the first shader does, like the initial brushstrokes?
That's a perfect analogy. Yes, the splat shader is exactly that. It's where the initial color and velocities get, well, pasted or splatted into the textures. Think about when something interacts with the fluid in a simulation, like maybe your mouse cursor moving through digital smoke or those colored balls in some demos.
Right.
The splat shader takes the movement data from those interacting objects, their position, how fast they moved from the last frame, and translates that into localized spots or splats of color and velocity within the fluid textures. It processes data from something called an object data texture, which tracks those interacting objects. It looks at the difference between current and previous positions to figure out the direction and force.
So it essentially injects the initial disturbance.
Exactly. It calculates the influence based on distance, applies force if needed, or mixes color. It's the very first step that sets the fluid in motion based on external interactions.
Okay, so we have these initial splats of motion and color. But fluids swirl, right? They form eddies and vortices. How does the simulation figure out where things are swirling?
Yes, the swirls. That's fundamental to making fluids look real. That job falls to the curl shader. Its whole purpose is to calculate something called vorticity, which is basically a measure of the local rotation or the swirliness at every point in the fluid.
Swirliness, I like that.
Hey, yeah, it's crucial because it helps create and maintain those characteristic swirly patterns you see in smoke or turbulent water. It doesn't guess, it mathematically derives it. It does this by looking at the velocity field, those invisible arrows in the immediate neighborhood of each point. It samples velocities from pixels left, right, top, and bottom. Then it does a calculation involving those samples to figure out the rotational tendency right there. This vorticity value gets stored, usually in a spare channel, like the alpha channel, of one of the textures.
Okay, so the curl shader finds the swirliness. But finding it is one thing. How does that swirliness actually affect the fluid? How does it make things move? Does it just sit there as data?
Great question. Knowing where the swirls are isn't enough, you're right. They need to do something. That's the role of the next shader, the vorticity shader. This one takes the swirliness value calculated by the curl shader and turns it into an actual force. This force then gets added back into the velocity field, so it modifies the existing motion. It essentially boosts the fluid's natural tendency to form and maintain those swirls. It computes a force vector based on differences in curl values nearby, normalizes it, scales it by how intense the swirl should be, and adds that force to the velocity considering the time step. It makes the simulation look much more dynamic, more alive.
That's really clever. Okay, so we have interaction, we have swirls feeding back into the motion. But what about keeping it realistic? Real fluids, like water, don't just puff up or shrink down out of nowhere. How's that handled?
You've hit on a critical aspect, incompressibility.
Right.
And that's where the divergence shader comes in. Its job is to compute the divergence of the velocity field.
Divergence, what's that exactly?
Divergence measures how much the fluid flow is spreading out or diverging from any given point, or the opposite, how much it's converging inward. For a fluid that we want to simulate as incompressible, like water or smoke generally, this divergence value should ideally be 0 everywhere, meaning no net flow out of or into any tiny region.
Right. Volume stays the same.
Exactly. So the divergence shader samples the velocities of neighboring points, carefully handling the boundaries so fluid doesn't magically leak out, and calculates this divergence value. It's basically checking, is the flow causing expansion or compression here? The result is stored for a later step.
Makes sense. But, in simulations, sometimes values can just keep building up and up, right? Wouldn't pressure or velocity just get infinitely large if you keep adding forces? How do you prevent things from going haywire or make smoke fade away?
That's a very practical concern, and you need a mechanism for that. Enter the clear shader. This one is simpler. It acts like a natural decay. Its job is to gradually reduce certain values in a texture over time. It multiplies a specific component, often pressure, by a decay factor less than 1.
So it just dials things back a bit each frame.
Pretty much. It helps clear or fade out things like pressure, preventing it from accumulating indefinitely, which could make the simulation unstable. Or it can be used on the dye texture to make smoke dissipate realistically. It just applies a decay uniform to fade things out gently.
Okay, so the divergence shader finds out if the fluid is trying to expand or compress. The clear shader helps keep things stable. But how do you actively fix that divergence problem and enforce the incompressibility?
Right. Identifying the problem isn't fixing it. The fix, the core of enforcing incompressibility, happens in the pressure shader. This one's a bit of a workhorse. Its goal is to figure out the pressure field throughout the fluid. Think of pressure as the internal force that pushes fluid from crowded areas to less crowded areas.
Like air escaping a balloon.
Exactly. By calculating the correct pressure at every point, the system can later adjust the velocities to counteract any divergence, forcing the fluid to behave incompressibly. Now, getting this pressure field right is tricky. Our sources mention that this pressure shader is actually run multiple times per frame in a loop.
Oh, really? Why multiple times?
It's an iterative refinement process. Each pass gets the pressure values close to the correct solution that ensures 0 divergence. It samples pressure from neighbors, considers the divergence calculated earlier, averages things out. Doing it multiple times, controlled by pressure iterations, makes the result much more accurate and stable.
Wow, okay. So it really works hard to get that pressure just right. Now we have accurate pressure and we have the fluid's velocity. How do these two finally come together to give us that perfect, non-expanding, realistic movement?
This is the final crucial step for incompressibility. The gradient subtract shader. A bit of a mouthful, but its job is vital. It takes the pressure field calculated by the pressure shader and computes the pressure gradient. The gradient is basically a vector field pointing in the direction of the steepest increase in pressure, and its length tells you how steep that increase is.
Okay.
Then it subtracts this pressure gradient vector from the current velocity vector at each point.
Subtracts it. Why subtract?
Because subtracting the gradient effectively removes the part of the velocity that causes divergence. It redirects the flow away from high-pressure areas towards low-pressure areas, precisely canceling out any tendency to expand or compress. This makes the final velocity field divergence-free or incompressible. It ensures volume is conserved.
That actually makes a lot of sense. You calculate where the pressure pushes, and then you adjust the flow to follow that push, canceling out the problems.
You got it.
All right, so after all that complex calculation, the splats, the swirls, finding divergence, fixing it with pressure, subtracting gradients, how do the actual visible bits, the color or the dye, actually move? This must be where you really see the flow happen, right?
Absolutely. This is the payoff, visually speaking.
Yeah.
The advect shader handles the advection step. Advection is just a fancy word for moving stuff along with the flow. This shader takes a quantity, could be the velocity field itself or the color dye texture, and transports it according to the final corrected velocity field we just calculated.
So it pushes the color along the velocity arrows.
Almost. It actually works backwards, which is more stable computationally. For any given point, it looks at the velocity there and asks, where would a particle at this point have come from in the last tiny time step? It then samples the quantity, color, or velocity from that calculated upstream location and assigns that value to the current point. It's like saying, my color now is whatever color was upstream a moment ago.
Huh, interesting. Working backwards.
Yeah, it avoids certain problems. This shader also often includes dissipation. It can slightly reduce the advected quantity over time, controlled by delta, time step, and a dissipation factor. This helps things like smoke gradually fade or ripples smooth out, adding another layer of realism and stability.
So putting it all together, this isn't just a single pass, right? You're saying these 8 shaders, splat, curl, vorticity, divergence, clear, pressure, gradient, subtract, advect, they run one after another really fast over and over.
Exactly. They execute sequentially inside the main update loop of the simulation, constantly refining the velocity field, solving for pressure, moving the color. And after each full cycle, the results are written to those ping-pong textures we talked about earlier. The output texture from this frame becomes the input source texture for the next frame, and they swap roles.
Ping pong, right.
Right. This continuous iterative process, managed by functions often called blit or similar, creates that smooth, evolving, dynamic motion you see. It's really a remarkable feat, breaking down incredibly complex physics into these manageable, super fast computational steps, perfect for a GPU.
And then the final results of the dye texture, that's what gets drawn on screen for us to see.
That's usually the case, yes. The final dye or T-dot texture becomes the visual map of our fluid.
And there you have it. Wow. A really deep dive into the algorithmic brushstrokes, painting fluids and smoke onto our screens. It's honestly incredible how breaking down something that complex, fluid dynamics, into these distinct shader steps leads to such stunning results.
It really is. It highlights how phenomena that seem incredibly complex, almost chaotic, can actually be simulated quite effectively through a series of these well-defined iterative calculations. Each shader plays its specific part, contributing step by step to the overall illusion of realistic fluid motion and interaction, from that very first splat to the final smooth flow. It's a great example of modular computation.
So what's the takeaway here? Well, the next time you see a plume of smoke rise in a game, or a river flow, or just water rippling, maybe you'll picture that intricate dance happening behind the scenes. Splat, curl, vorticity, divergence, clear, pressure, gradient, subtract, advect, all working together millions of times a second just to create that seamless visual for you. And maybe consider this. If something as complex as fluid dynamics can be modeled effectively using these kinds of iterative modular steps, what other complex systems, maybe natural ones or even social phenomena, could we better understand or simulate by breaking them down in a similar way? What new kinds of visual or interactive experiences could we unlock by applying this kind of thinking elsewhere? Something to think about.